For those of you that have ever stayed home and you were sick and you've watched The Price is Right, you have obviously seen the game that they call Plinko. And that's where you drop the thing down and it scatters back and forth and you're trying to get the money at the bottom, and then when they win, they shout. So what is actually going on here, and why do they design that game the way they do? Well, come to know a British member of the Royal Society named Sir Francis Galton, you can thank for coming up with this idea. And so to illustrate this point, we're just going to run a sample of, let's say if there's one, and let's speed it up, there's only one peg, it can go one of two ways. This is the perfect example to visualize our binomial. And it can go one, go to the other, 0, 1, 0, 1. And it should be roughly equal if each decision is a 50-50. This is just like a flip of a coin. But what happens instead of one? Let's say we have 3 levels. And I just hit restart. Now, as we increase the amount of levels, there's more choices that we should see. And each of those choices, if there's a 50-50 shot that it goes left or right, we should start seeing something a little more in the middle, where we have more opportunities for it to go down the middle and less on the tails. Well, let's say, for instance, this is after 100. We see 7 zeros, 32 ones, 45 twos, and 9 threes. Interesting. Well, what happens if we increase the size to, let's say, instead of 3 different levels of pegs, we have something that looks more like a Plinko board? Where do we anticipate these balls as they drop down and down and down to go? And if we let this run for a little bit, and we're just going to...
The fabulous 60-minute Price is Right.
So as we approach about 200 trials, we should start seeing something quite normal. And in fact, the more trials that we do, the more balls that drop and fall, we start seeing this type of normal distribution. And you might be saying to yourself, Mr. Swenson, why haven't we gotten an 8? Is it impossible for a ball to go all the way down that way? Well, we should start thinking in our normal distribution. Now, each one of these has a 50-50 shot of making a left or right decision. We've set it up that way. And because of that, we can use this new probability model known as a binomial. So after that brief and wonderful intro on the Galton board, we're going to be talking about probability models in Chapter 17 to wrap up everything we've talked about with probability and expected value and means and variance with Unit 4. So again, read the chapter, complete the reading notes, and do these homework problems as you see. So the objective that we're talking about is students recognize Bernoulli trials and calculate probabilities of various forms of success in Bernoulli trials. So if we were in class, we would do an odd or even activity. Of course, we can't do that. So I want to just jump into this based off of what we saw. The basis for the probability models we will examine in this chapter is the Bernoulli trial. We have Bernoulli trials if the following conditions are met. There are only 2 possible outcomes. Think left or right on the Galton board, or flipping a coin, head or tail, or make or miss. The probability of success is constant, so you know what the probability of getting a success is. The trials are independent. So again, if we are independent, then they are non-conditional. And then for binomial trials, there is a fixed number of trials. So this is not going on infinitely, but rather there is a time where this ends. If all of those conditions are met, and the AP test will ask you to justify many of these, then we can do a similar analysis. So with a Bernoulli trial, there are 2 types that we'll see, a binomial or a geometric. Binomial is what's the probability of getting X number of successes, and geometric is what's the probability until you get a first success. So one important requirement, one of the One of the important requirements for Bernoulli trials is that the trials are independent. We've looked at this many times when it comes to identifying if events are independent or not. When we don't have an infinite population, the trials are not independent. But there is a rule that allows us to continue as if we do have independent trials. And this is the 10% condition. I want you to get used to seeing this 10% condition because it comes up again and again and again and allows statisticians and mathematicians to justify saying things are independent, even though clearly they are not, or there is without, like we're not replacing things. Once you choose a person, you can't put them back into the pool to which to ask people questions. So the 10% condition says Bernoulli trials must be independent. If that assumption is violated, it is still acceptable to proceed as long as the sample is smaller than 10% of the population. So if we were working with all of the students that go to Divine Child, there's 880 this year that go to Divine Child roughly. So if we are under 88 people in our sample size, we can still classify those people as independent. So with a small subset of the population, the probabilities do not actually remain constant, and the events are not truly independent. But the differences are negligible, and thus trials are realistically sufficiently independent, and the probability is sufficiently constant. So what do I mean by that? Consider the case of domesticated dogs. In 2018, there were an estimated 80 million dogs in US homes. Of these, approximately 4 million are some form of a pit bull. A dog selected at random has a probability of being a pit bull 1 out of 20 million, or 0.05% of the time. Sorry, 0.05 or 5% of the time. If we were to select a second dog without replacing the original dog, once we pick one, then we pick another. Obviously, without replacement, they're not independent. Probabilities drop down. The probability of it being a pit bull would now be 3,999,999 out of 79,999,999, or 0.049999881, which is close enough for government work. Which is why when the sample size is large and we are under that 10% condition, they're roughly independent. So let's get into this first thing, this binomial. On your calculator, you'll see it as binom, nomial, and then the inputs are the number of trials, which is n, and the probability of success. So n, number of trials, and p, probability of success, whatever that means in this case. So the binomial model tells us the probability for a random variable that counts the number of successes in a fixed number of Bernoulli trials. Two parameters define the binomial, n, the number of trials, and p, the probability of success. We denote that binomial n, p. The second model that we will talk about is a geometric. And all you need to do is identify the number of successes. So geometric is just the probability of success. Geometric probability model tells us the probability for a random variable that counts the number of Bernoulli trials until we get the first success. Geometric models are completely specified by one parameter, p, the probability of success, and are denoted geometric p. Got it? Just so we recall, we've talked about factorials. We have talked about combinations. With factorials, we're talking about the number of ways to order. So the number of ways you can order 0 things is one way, you don't do anything. The number of ways you can order one thing is one way, you put it in front of you. 2 is 2 times 1, 3 factorials, 3 times 2 times 1, etc., etc. We utilize this to come up with the formula for combinations. When we are counting and arranging things, and order does not matter. If we wish to count the number of possible arrangements of the order when order is unimportant, we have this idea of combinations, which we've seen as NCR or N choose R. Or I've also told you that it's N and K, and we get our formula. So if we have a collection of 5 motorcycles and we want to wash 3 of them without concern of order, how many choices do we have on which the motorcycles to wash? Well, we have 5 factorial over 5 minus 3, or 2 factorial. This would be the number of permutations when order matters. And then we have an additional 3 factorial to take out the order. So there are 10 ways we can wash 3 of 5 motorcycles without regard to the order in which we choose them. We've talked about that. If you want, go back to the addendum videos if you need them. So with a binomial model, to keep the notation clear, we use the following conventions. For the probability of getting a success, instead of writing p parentheses s every time, we just write lowercase p. Lowercase p means probability of success. The probability of a fail, or the complement to success, we call q. P and q. To find the probability of success, you do 1 minus the probability of failing, or 1 minus q. The probability of finding a failure is 1 minus the probability of success, or 1 minus p. X is equal to the number of successes in the trial, so we say x is n. So the probability of some random variable getting x number of successes is the probability of exactly x number of successes out of n trials. For example, suppose we roll a die 4 times. Success, we're going to classify as rolling a 6. There are only 2 possible outcomes. Would you all agree that if you roll a die, you either get a 6 or you don't get a 6? So with 4 rolls, there are 16 possible results. And you can get 4 6s, or 3 6s, or 2 6s, or 1 6. But order doesn't matter because 6s are indistinguishable from each other. So what would be the probability of rolling exactly 1 6? Well, look at the number of things that we have. We are looking for the ones that have exactly 1 6 out of the total 16. Well, think about that. That's the probability of getting 1 out of 6, and then 5 out of 6 is a fail, and then 5 out of 6, then 5 out of 6. So all of those fails have to go just as much as getting the success. We also have to factor in that there's 4 ways of getting a success: the first spot, the second roll, the third roll, or the fourth roll. So the probability of getting 1 successful roll out of 4 rolls would be 125 plus 1296 plus 125 over 1296 plus 125 over 1296 plus 125 over 1296. So that would be 125 over 324 if we simplified that down. That's pretty cool. If you notice, that 4 ways of choosing them is our combination that comes into play. So in n trials, there are n choose k different ways of having a success. And we read this NCK as combination of n items choosing k of them, or n choose k. So put this all together. This gets complicated quickly if you're not keeping track of things. Thus, we make life easier by saying simply a binomial expansion. The probability of our random variable being x number of successes in n trials is n choose k. Probability of success of k, that's the number we want, and then the number of fails is n minus k. And this is the probability of exactly x number of successes out of n trials. I know this seems a little gibberishy, but this actually makes a lot of sense. The probability of exactly x number of successes out of n trials is our formula. So to understand the formula, let us look at the components. The number of ways we can get x successes out of n trials is simply the combination of n results taken x at a time. So that is our combination part. The first component of the formula is the number of ways exactly x successes we can get. That's the ordering part. Then the next piece, the p of x and the q of x, are the probability of successes. And then however many successes we get, we also get fails. We have to have both. That's why it's a binomial. The probability of each individual sequence of x successes and failures is the product of the probabilities because they're independent. In this case, it would be p to the x times q to the n minus x. So back to the probability of rolling exactly 1 6 in 4 rolls. We want 1 6 in 4 rolls. So we want 4, choose one of them. We want 1 6th to the first power, and then 5 6ths to the 4 minus 1, which is 3. And if we type that in, then we also see that we get the same probability. Now we could, if you really wanted to, go back to writing out a tree diagram and listing out all of these. And for a binomial, p must remain constant. So let's pretend the probability of getting a boy in our example that we did a long time ago is 0.51. So you have your first child, 0.51 for a boy, 0.49 for a girl. Then the second child, 0.51, then 0.49. Then the third child, 0.51, 49, 0.51, 49, 0.51, 49. And to get all of this binomial distribution of boy or girl each time, we multiply those probabilities and add them up. Now notice, the probability of getting 3 boys is 3 choose 0, which is 1, 0.513 to the third, 0.490 to the 0th power, which is 1. And if we did 2 boys, it would be 3 choose 2. If we did 1 boy, it would be 3 choose 1. If we did 0 boys, it would be 3 choose 0, and the probabilities would reverse. This is our binomial expansion with 3 boys. And if you look, all of these values will fill out this table of 0 boys, 1 boy, 2 boys, and 3 boys, provided that we just follow our binomial distribution. So a probability distribution of the number of successes when there are only 2 outcomes is simply a binomial distribution. Binomial just meaning 2 terms, 2 outcomes, a yes or a no, a boy or a girl, a head or a tail, a 6 or not a 6, lights on or lights off. The outcomes of a binomial experiment and the corresponding probabilities of these outcomes make up a binomial distribution. And so we list out the binomial distribution as this number of successes we get x, and then the probability on the right-hand side in sort of a tabular form. So for example, rolling a die 4 times, we have the probability of getting 0, 4, or getting 0 6s, then 1 6, then 2 6, then 3 6, then 4 6. And as we see, the probability of getting 0 is pretty high because that's not a success, not a 6. And then the further we go, the less likely we are to not get that number. It's more likely to be balanced out. So in the next video, we're going to pick up with this problem and we're going to showcase how to use your calculator. So again, we're looking at binomial distributions, how to get these numbers relatively easy, and then we'll move on to geometric. See you in the next one, Falcons.